Welcome dear learners. We are continuing Unit 4 Fundamentals of Analytical Chemistry. In the present module, we are discussing theory of acid-base titrations. The contents of this module are volumetric analysis, different types of titrations, neutralization reactions, introduction to acidimetry and alkalimetry, common indicators, selected acid-base titrations, and problems based on these concepts. First of all, we are taking volumetric analysis. Here we are just taking volumetric analysis for the sake of revising the concepts that we learned in the previous module. Volumetric analysis is a quantitative analytical method used to determine the concentration of an unknown solution by reacting it with solutions of known concentration. That means it is very well clear that in volumetric analysis there are two kinds of solutions. One solution with exactly known concentration and other one with the unknown concentration. We are reacting these two substances together, and by measuring the volume, it is possible to calculate the concentration of the unknown material with the known concentration of the other substance. This volumetric analysis involves measuring of the volume of the reagent, that is called the titrant, required to complete the reaction with the analyte. So in volumetric analysis, there is one titrant, that is a solution with exactly known concentration, and the other one is called analyte, whose concentration is to be determined. So you are performing the volume measurement in the reaction between a titrant and an analyte. Now, principle and procedure of volumetric analysis. It should be noted that the basic principle behind volumetric analysis is number of milli-equivalents of the analyte solution should be same as that of the titrant. That is, number of milli-equivalents of the titrant and number of milli-equivalents of the analyte are the same. Number of milli-equivalents can be calculated by using the expression number of milli-equivalents equal to normality into volume in ml. Therefore, in volumetric analysis, the most commonly used concentration term is normality. Whenever you are multiplying normality with the volume of the solution in ml, you will get the number of milli-equivalents. The number of milli-equivalents of the first component should be same as number of milli-equivalents of the second component. Or there are two reagents in volumetric analysis. The number of milli-equivalents of the first reagent should be same as the number of milli-equivalents of the second reagent. That is, we can write N1 V1 equal to N2 V2. This is otherwise called the volumetric formula or volumetric equation. Here N1 and V1 represents normality and volume of solution 1, that is nothing but analyte. N2 and V2 represents normality and volume of solution 2, that is nothing but titrant. That is, number of milli-equivalents of the titrant should be same as number of milli-equivalents of the analyte. This is the very basic principle of volumetric analysis. Moving on to the procedure of volumetric analysis. In the practical work, we are first taking a known volume of the solution of unknown concentration, that is nothing but analyte, is taken with the help of a pipette and place it in a conical flask. That is, we are taking the analyte solution, definite volume of which is taken by the pipette and placed it in a vessel called the conical flask. A solution of known concentration, that is called the titrant or the standard solution, is added from the burette until the reaction is complete. The point at which the reaction is complete is known as the end point. And to find out that end point, we are using some reagent called, or the end point is detected by using substance called indicator. The reaction is based on, the reaction between analyte and the titrant is based on a balanced chemical equation, and the concentration of the unknown solution is calculated using the titration formula, which is nothing but N1 V1 equal to N2 V2. Now we are considering different types of Titrations. We heard this title in the previous module, and in this module we have to focus on acid-base titration. Prior to that, we are just have an overview of different type of titration as a revision concept. So, the various type of titrations include the following. First one, that is nothing but acid-base titration. Based on neutralization reactions between an acid and a base, this titration, that is acid-base titration, will work. That is, there occur some neutralization between an acid and a base during the course of acid-base titration. Indicators like phenolphthalein, methyl orange, etc. are used in acid-base titration. A common example of such an acid-base titration is titration of sodium hydroxide against HCl. It is clear that sodium hydroxide is a base, HCl is an acid. The reaction between them leads to the formation of a salt and water. Such a kind of reaction is called neutralization reaction, and acid-base titrations are based on neutralization reactions. Now, the second category of titration is nothing but the redox titration. As the name indicates, there occurs some redox reaction. Redox reaction is the reaction between an oxidizing agent and a reducing agent. And this redox titration is based on oxidation reduction reactions. There occur oxidation as well as reduction, such that you can call it as a redox titration. And redox titration involves electron transfer between species. They are nothing but oxidizing agent and reducing agent. During the course of the reaction, oxidizing agent will undergo reduction and reducing agent will undergo oxidation. And typical example for such a redox titration is here. It is the titration between potassium permanganate and iron 2 plus ion, preferably from ferrous sulfate or more salt, etc. In this reaction, KMnO4 acts as an oxidizing agent and Fe2 plus acts as the reducing agent. Now, the third category of titration is nothing but complexometric titration. As the name indicates, in complexometric titration, there do occur some complex formation. That means there do occur the formation of a coordination complex in complexometric titration. For the formation of the coordination complex, there must have metal ions as well as ligands. In complexometric titration, the most popularly used ligand is a chelating ligand, that is nothing but ethylene diamine tetraacetic acid or EDTA. So, in complexometric titration, there occurs some complexation reaction, and based on formation of a complex between metal ions and ligands is the basis of complexometric titration. And such kind of titration utilizes indicators like ureochrome black tea, muroxide, etc. Now, a typical example for such a complexometric titration is here. It is nothing but the titration between ethylene diamine tetraacetic acid with is a chelating complexing agent against calcium 2 plus ion. That is, in this special type of titration, or in the titration between EDTA against calcium 2 plus, there occur the complexation between EDTA and calcium 2 plus, or calcium undergo complexation with ethylene diamine tetraacetic acid. Now, we are entering into the last category of titration, that is nothing but precipitation titration. As the name indicates, there do occur some precipitation reaction between two reagents. And this precipitation titration is based on the formation of a precipitate. Silver nitrate or AgNO3 is commonly used reagent in the precipitation titration. For example, you can titrate silver nitrate against NaCl. During the course of the reaction between AgNO3 and NaCl, there occur the formation of a white curdy precipitate, that is nothing but silver chloride. Based on that precipitate formation, you can assess the concentration of one of the reagent among these. So, that about the precipitation titration. So, we have discussed different type of popular titrations that we adopted in volumetric analysis. Now, we are entering into more details of acid-base titration, and prior to discuss that acid-base titration in more detail, first of all, we can have a knowledge on, we must have a knowledge on neutralization reactions. Now, what are neutralization reactions? A neutralization reaction is a type of chemical reaction in which an acid and a base react to form water and a salt. This reaction typically occurs in aqueous solutions and involves the combination of H plus ions from the acid and OH minus ions from the base to form water. Acid is an H plus ion donor. That's why HCl acts as an acid. H2SO4 acts as an acid. They can donate H plus ions. A base is an OH minus ion donor or hydroxide ion donor. So when a base combines with an acid, there occur the combination of OH minus and H plus ions to produce the water molecule. Such a kind of reaction is considered as a neutralization reaction. Now, general equation for neutralization reaction is this, that is acid plus base gives salt and water. I will just show you the reaction between sodium hydroxide. Let the acid be hydrochloric acid HCl and let the base be NaOH. It enables the formation of salt, that is nothing but NaCl. In addition to this, water is also produced. So this reaction is considered as a neutralization reaction. Now, the acids may be strong acid like HCl or H2SO4, weak acid like acetic acid. The base may be strong base like NaOH or KOH and weak base like NH4OH. So it implies that acids are two types, strong acid, weak acid. Bases are two types, strong base, weak base. These are the examples for strong acids and strong bases, weak acids as well as weak bases. So which part differentiate between strong and weak acids and bases? It is based on ionization. A strong acid or a strong base will undergo 100% ionization, but a weak acid or a weak base will undergo only partial ionization. So this classification, strong or weak, acids or base, depending on their extent of ionization. This is an important point that you have to keep in mind. Now, since there are two kinds of acids and two kinds of bases, there are four probable neutralization reactions. And now we can enter into different types of neutralization reactions. We learned that there are two kinds of acids, strong acids and weak acids. There are also two kinds of bases, strong bases and weak bases. Thus, there is a possibility for four types of neutralization reactions. A neutralization reaction is between an acid and a base. Acid may be strong or weak. Base may be strong or weak. So there are four types of neutralization reactions, out of which the first one is the neutralization reaction between strong acid and strong base. That is SA plus SB. Strong acid is abbreviated as SA. Strong base is abbreviated as SB. A typical example for such a strong acid strong base titration is here. That is HCl against NaOH. In this reaction, HCl is strong acid, NaOH is strong base, and NaCl is the salt, and the side product is water. The products are neutral, salt and water. The pH of the final solution is around 7 since the obtained salt is neutral. The second category of the neutralization reaction is between a strong acid and a weak base, that is SA plus WB. A typical example is HCl plus ammonia. Ammonia or NH4OH is a very weak base. HCl plus ammonia produces NH4Cl. Here I am not showing the formation of water. To get the formation of water, you have to take NH4OH instead of NH3. In that situation, you can write the expression as HCl plus NH4OH gives NH4Cl plus water. So, this ammonia gas on reaction with the water produces NH4OH, that is liquor ammonia. Ammonia as well as NH4OH, both are bases, both are weak bases. So, the reaction between HCl and ammonia can be considered as a reaction between a strong acid and a weak base. This produces an acid salt, that is ammonium chloride, and the final pH is less than 7. This is because ammonium chloride on dissociation produces ammonium hydroxide and HCl. HCl being a strong acid, so acidic strength dominates and pH must be less than 7. That is the concept. Now, we are discussing the third type of neutralization reaction, that is the reaction between a weak acid and a strong base, abbreviated as WA plus SB. A typical example for such a titration is acetic acid plus NaOH produces CH3COO, Na and water, and this produces a basic salt, that is sodium acetate. Sodium acetate on hydrolysis produces sodium hydroxide and acetic acid. That sodium hydroxide is more basic, so the pH of the medium will be greater than 7. And the last category of neutralization titration is here. It is the neutralization reaction between weak acid and weak base, that is WA plus WB. The typical example for such a reaction is CH3COOH plus NH3 to get CH3COO NH4. Here also you will get water if you are taking NH4OH instead of ammonia. Then you can write the expression as CH3COOH plus NH4OH produces CH3COO NH4 plus water. And this neutralization reaction between a weak acid and a weak base produces a salt with variable pH depending on the strength of the acid and base initially taken. That all about 4 types of neutralization reactions. Now we are entering into acidimetry and alkalimetry. The titration, the volumetric analysis involving acids and bases are collectively known under the heading acidimetry and alkalimetry. Now we can have an introduction about acidimetry and alkalimetry. This belongs to acid-base titrations of volumetric analysis. Acidimetry and alkalimetry are broad names which involves acids as well as bases in volumetric analysis, and we are entering into more details of acidimetry and alkalimetry. Acidimetry and alkalimetry refers to titrations involving acids and bases in volumetric analysis. This point is very relevant. They refers to titration involving acids and bases in volumetric analysis. First of all, we can take acidimetry. Acidimetry is the quantitative analysis of basic or alkaline substance using a standard acid solution. So, in acidimetry, we use a standard solution of an acid to estimate the concentration of a base. And in alkalimetry, which is a quantitative analysis of an acidic substance using a standard base solution. So, in alkalimetry, we are using a standard solution of a base to evaluate the concentration, unknown concentration of an acid. So, this is about the difference between acidimetry and alkalimetry. So, in acidimetry, we are using standard solution of acid. In alkalimetry, we are using standard solution of an alkali, that is nothing but base. Now, the basic principle of acidimetry as well as alkalimetry is neutralization. Neutralization means the reaction between an acid and a base to produce salt and solvent, salt and water. Such neutralization reaction is the basic principle of acidimetry and alkalimetry. In acidimetry and alkalimetry, there is also equivalence point. The point at which the amount of acid equal to the amount of the base in the reaction is known as the equivalence point. But equivalence point is a point which cannot be determined experimentally, but only theoretical determination is possible. However, instead of finding out the equivalence point, we are finding out the end point, which is a mere indication of the equivalence point, and end point can be evaluated with the help of indicators. That is, end point is the point at which the indicator changes color, signaling the completion of the reaction. Now, various steps we adopted in titrations involving acids and bases, or various steps in acidimetry and alkalimetry are described here. The first step is the preparation of the standard solution. The second step is the filling of the burette. And you should remember, the standard solution is prepared by taking a substance called the primary standard, weigh it accurately, transferred it into a standard volumetric flask and made up to the mark, such that you will get a standard solution. Take that standard solution and fill it in the burette. That is the second step. In the third step, you are pipetting out the sample solution or the analyte solution, and this solution should be taken in a conical flask, and then you have to add some indicator, and then you are performing the titration process. Titration process is the process in which you are draining the burette which contain the standard solution into the conical flask which contain the analyte solution. That process is called the titration process, and you are continuing the titration process till the end, till we reach at the end point with the help of the indicators. And finally, calculation of unknown concentration by using the formula we learned earlier, that is nothing but N on V1 equal to N to V2, that is the volumetric formula. Now, calculation of unknown concentration. This is very important as far as the acidimetry and alkalimetry is concerned. In acidimetry and alkalimetry, being volumetric analysis, which is a quantitative analysis, we have to get to the exact concentration of the unknown substance, for which we should remember every equations and concept behind the reaction for getting the exact value of the unknown concentration. The unknown concentration can be calculated by using the formula. This is nothing but the formula we learned earlier, N on V1 equal to N to V2, and more specifically speaking, N1 represents normality of the acid, V1 represents volume of that acid, N2 corresponds to normality of the base, and V2 corresponds to volume of that base. So, N on V1 equal to N to V2. 1 represents acid and 2 represents base. From this formula itself, it is very clear that the milliequivalents, number of milliequivalents of acid should be same as number of milliequivalents of base. This is very, very important as far as the basic principle of acidimetry and alkalimetry is concerned. Now, we are looking on to common indicators that we are using in acidimetry and alkalimetry, or indicators used in acid-base titrations. We have to give emphasis to acid-base indicators. But before entering into the details of acid-base indicators, we must have revised the concept of indicators and the general type of all indicators. So, indicators are substances that change color at a specific pH or at the end point of a reaction. They help in visually identifying the completion of a titration. There are so many type of indicators. Our aim is to focus on acid-base indicator. Even though that is the case, we have to just go through various kind of indicators as a revision. So, acid-base indicator is the first category. Change color at different pH values. Typical examples involve methyl orange and phenolphthalein. Another category of indicator is redox indicator. They change color due to change in oxidation state. Typical examples involves ferroin, diphenylamine. Another category of indicator is complexometric indicator. They are the indicators used in complexometric titrations, and this complexometric indicators are exemplified by eriochrome black tea as well as murexide. These are two important compounds which are used as indicators in complexometric titration, that is, they are complexometric indicators. The last category of indicators are adsorption indicators, and they are used in precipitation titrations by adsorption on the precipitate. Typical examples of adsorption indicators include fluorescein and eosin. Now, we are coming to the more specified acid-base indicators. Now, we are discussing common acid-base indicators. In this area, we will discuss the selection of the indicators and which indicator is suitable for a particular acid-base titration, etc. So, this part of the discussion is more prominent as far as the selection of indicators for an acid-base reaction is concerned. Now, methyl orange and phenolphthalein are commonly used acid-base indicators. This about their pH range and color change, etc. The first column represents the indicator. Indicators are methyl orange and phenolphthalein. Second column represents their corresponding pH range, and the last column represents the color change from base to acid medium. So, methyl orange lies in the pH range of 3.1 to 4.4, and its color change is from yellow to red. That means yellow in base medium and red in acid medium. And the second indicator is nothing but phenolphthalein. Phenolphthalein has a pH range of 8.3 to 10, that it works in a basic pH range. It is 8.3 to 10, 10.0, and the color change is pink to colorless. Remember, pink is in basic medium and colorless, that is colorless in acid medium. So, these about two popular acid-base indicators, nothing but methyl orange and phenolphthalein. Now, we can have more details about these two indicators, methyl orange and phenolphthalein. First of all, methyl orange. Methyl orange is an azo dye. Azo dye means it contains the coloring group N double bond N, that is nothing but the azo group. So, methyl orange is an azo dye and it contains an azo group. This is specifically diazo group, N double bond N or azo bond. This bond or this group is responsible for its color change. The molecular formula of the methyl orange molecule is here. It is C14H14N3SO3Na. So, it is a sulfate salt. It is a salt. That's why sodium is present here. And the structure of methyl orange is shown here. From the structure itself, it is clear that sodium exists as sodium ion. SO3 group you can see there. So, SO3 minus and Na plus. So, it is a sulfate salt. Moreover, you can see the presence of the coloring group, that is diazo group. So, one more nitrogen is present as a tertiary amine part, and this about the structure of the molecule, that is nothing but methyl orange. Now, moving on to the color change. Methyl orange shows color change from red in acidic solution and to yellow in basic solution. This about the color change. Two different colors can be seen. One is in acid medium and the next one is in basic medium. And methyl orange can be used for two kind of titrations. They are nothing but SASB titration, that is strong acid strong base titration, and SAWB titration, that is the strong acid against weak base titration. Moving on to the second most popular indicator, that is nothing but phenolphthalein. Phenolphthalein is a triaryl methane dye. It is an organic dye, and its color change is due to structural changes that happens in response to the pH change. So, as the pH changes, there occur some structural changes that enable color change. The molecular formula of the phenolphthalein molecule is here. It is a C20H14 oxygen 4, that is O4. The structure of phenolphthalein is shown here. You can see that it is a triaryl methane dye, and this about the phenolphthalein. Phenolphthalein shows the color change with respect to change in pH. Now, the color change of phenolphthalein is depicted here. Phenolphthalein is colorless in acidic solution and turns to pink in basic solution. This about the color changes. The pink color is in the alkaline or basic solution, and in acid medium it is colorless. This phenolphthalein is a good indicator which can be preferably used for titrations such as strong acid against strong base and weak acid against strong base. Thus, we have discussed two important type of acid-base indicators and the titrations in which they are used along with their color change. Now, indicator selection. This is very, very important as far as the acidometry and alkalimetry are concerned. Whenever you are doing some titration, you may have a weak acid or weak base, strong acid or strong base. Depending on the titration, you have to select suitable indicators, and we are now focusing on such indicator selection. This is the titration. These only three kind of titrations are shown here, even though there are four possible titrations. Only three kind of titrations, corresponding indicators and endpoint or color change is also shown, and endpoint pH is also shown here. So, In the titration type, the first category is SA against SB, that is strong acid against strong base. Here you can use both indicators. That means phenolphthalein or methyl orange can be used, and the end point has a neutral pH that is equal to 7. For titration between strong acid and weak base, you can use methyl orange, or methyl orange is the apt indicator and the pH must be less than 7. However, the titration between weak acid and strong base, the indicator is phenolphthalein. The indicator you should use is phenolphthalein, and at the end point the pH should be greater than 7. That is why the basic pH. In this chart, there is no mention about weak acid weak base titration. This is because for a titration between weak acid and a weak base, there is no visible indicator. A weak acid can be titrated with the help of a weak base through instrumental methods and higher advanced methods like conductometric titration, like pH metric titration, etc. That is far beyond the scope of this discussion. So, you have to keep this point in mind. Only 3 kind of titrations are possible. That means weak acid weak base titration is not possible in acidometry and alkalimetry. That is because there is no visible indicator for such a kind of titration. Now, this point I already discussed. No indicators are used for weak acid weak base titration, and we resort other methods to find out the end point. Now, selected acid base titrations. Strong acid against strong base titration or SA against SB titration. Typical example is the titration between hydrochloric acid and sodium hydroxide. The reaction is shown here. HCl plus NaOH produces NaCl and water. The indicator you can use 2 kind of indicator, either phenolphthalein with the color change from pink to colorless, and you can use methyl orange indicator where the color change is from yellow to red. This is the color change from the basic medium to acid medium. And the second category of second type of acid base titration is strong acid against weak base titration, abbreviated as SA against WB. Here, typical example is hydrochloric acid can be titrated against sodium carbonate, which is a weak base. This is the expression responsible for the titration. Na2CO3 plus 2 HCl gives 2 NaCl plus carbon dioxide plus water. So, indicator selected here is only methyl orange. Since the base is weak, you can select methyl orange, that we learned from the indicator selection, and the color change is from yellow to red. And the third category or third selected type of acid base titration is weak acid against strong base titration, that is WA against SB. Typical example is oxalic acid against sodium hydroxide, and the reaction between oxalic acid and sodium hydroxide is here. H2C2O4 plus 2 NaOH gives Na2C2O4 plus 2 molecules of water. And indicator you can select phenolphthalein, or phenolphthalein is selected as the indicator with the color change from pink to colorless. Now we can have some problems based on the concept learned. This is the first MCQ. Which of the following steps would help improve the accuracy of a standardization process in volumetric analysis? Using secondary standard with known molarity, boiling the titration solution to remove dissolved oxygen, ensuring that the pipette and the burette are rinsed with the distilled water before use, using primary standard with high purity and stability. It is very well clear that your answer is option D. You have to use or using primary standard with high purity and stability. Now the next MCQ. Why phenolphthalein is preferred over methyl orange in the titration of a weak acid with a strong base? Phenolphthalein changes the color in a basic pH range matching the equivalence point. Methyl orange has a color change too close to neutral pH. Phenolphthalein prevents overshooting of the end point. Methyl orange is unstable in aqueous solution. Your answer is option A. That is, phenolphthalein changes color in basic pH range matching the equivalence point. This is the third MCQ. Which of the following is an important consideration when selecting a primary standard for acidimetry. These are the options. The substance should be volatile. It should have a high molecular mass to minimize weighing errors. It should be hygroscopic. It should react with the oxygen in air. Definitely it is clear that option B is your answer. It should have high molecular mass to minimize weighing errors. Now, next MCQ. The volume of 0.1 molar HCl required to neutralize 20 ml solution of 0.125 normal sodium carbonate is. For HCl molecule, normality same as molarity, so you can take it as normality or molarity, both are same since HCl has an equivalent weight same as molar mass or molecular weight. Now these are the options in front of you. Option A 20 ml, option B 25 ml, option C 10 ml, and the last option is 12.5 ml. On careful analysis, you can arrive at the fact that your answer will be option B. This you can calculate by using the simple expression N1V1 equal to N2V2. Here you are calculating the volume of acid by knowing the volume and concentration of the base. So, by putting 0.1 normal as the acid into its volume equal to 20 into 0.125, or the required volume is equal to 20 into 0.125 divided by 0.1, the answer will be option B, that is equal to 25 ml. Now this is another MCQ. 20 ml of 0.1 normal sodium carbonate solution was neutralized by 18 ml of HCl. What is the concentration of HCl? Here also in this procedure, N1V1 equal to N2V2 is the base equation. By knowing the concentrations, you can find out the volume, and by knowing the volumes, you can find out the unknown concentration. From this equation, N1V1 equal to N2V2. These are the options: 0.1 normal, 0.11 normal, 0.2 normal, and 0.22 normal. By adopting the equation N1V1 equal to N2V2, you can arrive at the final answer as option B, that is 0.11 normal. This is the last MCQ of this module. 5.3 gram of sodium carbonate dissolved in 250 ml water to get a solution. The normality of the solution will be. This is a direct problem. You can calculate normality by using the expression mass of the solute divided by equivalent mass of the solute by volume in ml multiplied with 100. You will get the normality of the solution, and the options are option A 0.4 normal, option B 4 normal, option C 0.5 normal, and option D 5.3 normal. On careful substitution in that expression for normality, we will get to the final answer as option A, that is equal to 0.4 normal. That all about the present module. Have a nice learning experience. Thank you.